So good afternoon. For the benefit of those students who attend the class on time, so out of 56, I have 11 students now. It is 12:31. So for the benefit of those who attend on time, I should start now. We will continue to discuss the physics of molecules. This last part of the module is related to including the nuclear motion into the consideration. Thereby, at the end, we will see the allowed energies for the molecule as a whole is actually consisting of several terms. We have discussed the bonding due to electron distribution. So there's some typical binding curve, and then today we will consider the vibrational motion and the rotational motion of the nuclei. In particular, we will focus on diatomic molecules, which are the simplest examples. And only after that, we have this full molecular states. The wave function of the molecular states actually has three parts. The electronic wave function we already discussed. There will be a vibrational part of the wave function and a rotational part of the wave function. Fortunately, if we make sufficient approximations, these two parts are problems that you have already done. This is a harmonic oscillator in one dimension, and this is a three-dimensional rigid rotor problem. The nuclear wave function consists of these two rotational and vibrational motions combined. The last part of this discussion is related to how transitions can be made in different, what frequency range we should use if we want to excite rotational states or we want to excite vibrational state, what frequency we should apply, the light, I mean. And that leads to molecular spectrum. The last thing we will discuss is how to extract useful information from rotational and vibrational spectrum of a molecule. We will find that we can read out, well, read out means read and then do some very simple calculation, the bond lengths and how much energy is gained. So it is represented by the bond strength. Here it is the spring constant of the bond. So let's move on. So that is the big picture. So once upon a time, I think I also sketched this graph. So we do the electronic Schrödinger equation, and then we use Born-Oppenheimer approximation, meaning we fix an R and don't let it move, solve the electron, we try another R, and so on. At the end, we will have some bonding curve from which we can read out useful information. For example, this distance to the minimum will be the equilibrium separation between two nuclei in the molecule. Therefore, this is the bond length. And then, how much energy is gained relative to two neutral atoms far apart? That is the dissociation energy or the binding energy of the molecule. So this comes out from the electronic problem. Today, we will focus on one binding curve and then allow the nuclear motion to come in so that the nuclear may be doing some vibration to and fro around R0. And then it is a 3D molecule. So it is like a rod with two atoms on the two ends. It can rotate freely but like a rigid rod, and that is the rotational part of the problem. So let's recap what we did for the electron part. For the electronic part, we said nuclei don't move, so we don't have the kinetic energy term of the two nuclei, although we already did the center of mass, so it is a relative motion, but we ignore that kinetic energy, and then we focus on this electronic problem. Now it is time to take that equation out again and put back the nuclear relative motion. So mu here is the reduced mass of nuclear A and nuclear B, or atom A or atom B. The electrons are very light, after all, so dominated by the nuclear masses. So mu is the reduced mass, and this R is the relative separation from atom A pointing to atom B. For the electronic part problem, we have been ignoring it, okay? And then we solve this equals electronic part times its own wave function. So we did that, okay? But the whole Schrödinger equation actually has this kinetic energy term of the nuclei, then plus this electronic Hamiltonian, and then because we do Born-Oppenheimer, then we can use separation of the electronic variable and the nuclear variable. That's why we have a product of the wave functions to form the whole molecular wave function. So this was where we apply the Born-Oppenheimer and then focus on the electronic part in part 1 of our discussion. So now we take the same equation out, we put back the kinetic energy term of the nuclei. So this is the Schrödinger equation as a whole. The technical thing now is, once upon a time, we take R as a parameter. Now, when we put back this kinetic energy term, this is the conjugate momentum to R. Thereby, we now re-recognize R is a position operator of the nuclear motion, and then the gradient R over mu, okay, that is P over M, that is P over 2M, that is the P squared over 2M, that is the, so the gradient of R is the moment related to the momentum operator of the nuclear motion. So we put that in, and then we now do the quantum mechanics of the nuclear motion again, after solving the electronic part, having the bond already established. Okay, so that is exactly the idea behind Born-Oppenheimer approximation. So let's do a few lines of quantum mechanics. In part 1, we single out the electronic problem. So this is H electronic part times the electronic part of the wave function. We have done that. So fortunately, this part equals the binding curve, the eigenvalue, times the electronic wave function itself. All right. So therefore, when we see H electron, the electron wave function, we could substitute this thing in. And we did this equation by introducing another very important approximation, LCAO, MO, and then we have all the bondings, single, triple, double, pi, sigma, everything, okay? So that is a triumph of quantum mechanics. So now, when we see this, we plug this, okay? So therefore, we have the binding curve times the electronic wave function. The right-hand side is still the whole eigenvalue, the allowed energies of the molecule times the molecular wave function, which is a product of two parts. So therefore, suddenly, we have this two electronic wave function on both sides. So canceling it, we have a nuclear motion Schrödinger equation to play with. Okay. The key concept here, again, I stress it in part one, giving you the big picture. It is the electrons that is providing this binding curve. Now it appears as a potential energy function for the nuclei to move in. Okay, so the electron distribute themselves, providing a potential energy landscape in which the nuclear motion can be investigated. So that is the physical picture emerging from this equation. Do you understand? It is a highly non-trivial business. But by the end of year 3, you are mature enough for doing this kind of thing. This E of electron, okay, is a different problem, but now it plays another role. It set up the potential landscape in 3D for the nuclei motion to execute itself, okay? So this is exactly the problem that I use a cartoon to show you what it is. So we have the binding curve. We will usually take the lowest one because anything high there will be 10 EVs high, okay? So we only work at room temperature, things like that. Usually it is the lowest electronic curve that matters. And I think this is a very good picture to think about it. You cut it, okay? This is a 2D version. You can think of a 3D hot pot. I don't know how to draw it, but it is, in any direction out there, there's a rim, okay? So it is quite like this, and thereby it is easy to think of a marble being put down there, okay? So in the radial direction, there will be some oscillating behavior that will be vibrational problem, you see? But along the rim, there's the bottom of the pot, the marble could rotate, and that is the rotational problem. That is the 2D analogy, all right? Now extend it to 3D. So it is a 3D relative motion problem. We have R, theta, and phi, well, in capital letter, okay? To signify it is nuclear motion, and there's a phi as well. So you have two angles and a radial distance. In general, this vibrational motion and the rotational motion they are coupled, okay? I mean, in the casino, okay, the marble goes in, usually the motion of the marble is something like it rotates, it also vibrates. So the vibrational problem is coupled with the rotational problem. And that will make life harder than what we will discuss. Therefore, we will make further approximations to decouple the vibrational and rotational motion, at least as a lowest order approximation to get some meaningful result that can be compared with experimental data. So it is good to have a 2D picture in mind before we jump into the 3D version of the problem. So in 2D top view, you have this rotational motion that is the angular problem. At the bottom of the rim, just go on rotating. Then you will have a side view that could have a vibrational motion. So in a 2D analogy, we already get a sense. If we decouple the two things, life will be much easier. A rotor in classical mechanics will have energy angular momentum square divided by 2 times something called the moments of inertia. I hope that you realize I have some problem. I can't write. Okay. I hope that you realize mass times this separation square is the moment of inertia. And that is what you know from classical physics, year 1 physics, rotational motion. You also know in quantum mechanics, it is very easy to treat L squared. It simply becomes L times L plus 1 h bar squared. So if you go to quantum mechanics, it is this. And down there, actually, it is the moment of inertia. Okay, so rotational motion will pose no problem whatsoever to us. We know how to do that. Now, how can I erase this? I need some way to. How can I erase this? Anybody knows? Okay. Okay. Complicated. So let's move on. So with this big picture, we can almost immediately write down the answer. So let's further develop the solution. So this is the nuclear problem that we want to solve. It is a single particle 3-dimensional problem. We would also assume this potential energy profile to be spherically symmetrical to make life easier. All right. So now we know this thing in the radial direction has this profile. But from experimental observation, we know vibrations will not be of big amplitude away from the equilibrium separation. These bonds are very stiff, okay? Covalent bonds, things like that. So the vibration will only be around the equilibrium separation by a little bit. Thereby, it is very okay to focus on the part near the bottom of the binding curve. I will call the bottom of this energy E electron at the equilibrium separation. So it is just a number. It refers to this value, okay? So from here, you go to the left, you go in a little bit, you go out a little bit. It is like a parabola. So near a minimum, there is always, the leading term is quadratic. So technically, you do a Taylor expansion. It is only about the radial direction. So R near R0. So I'm thinking about places here and places there. All right. So this is the bottom value. The first order term is 0 because force is 0 there. Slope is 0, flat. Okay. No force. That's what equilibrium means, right? And then the leading order will be second order. The second order things means the second derivatives of this binding curve gives you the spring constant of the bond. And that will represent how strong or how stiff that bond is. Remember, K bigger, the parabola is like this. Spring constant smaller, the parabola is like that. All right, so that matters. That will be different for different molecules. So that is the K. And then it goes like R minus R0 square. Okay, now take note of this. It is away from the center where atom A sits. So we are talking about how B vibrates relative to the position of A. Okay, so it is about the equilibrium separation. R minus R0. Okay, so now plug this expansion. There are two terms into equation 48. Okay, this is just a number, remember. Okay, now it is just a number, therefore after plugging in, I can put it to the other side. Okay, just a number, I take care of it later. Okay, so here is the Schrödinger equation, still three-dimensional Schrödinger equation. So here, if you want to do a little bit more in mathematics, go through the solution. This page is optional, right, and follow, okay? But if you want to look at how at the end we have these three terms in the energy, this is how things goes. And by going through that more carefully than I do here, you will discover what terms have been neglected. Okay, it is not an easy question and not an easy answer. If you want to ask, what are the terms being ignored? Okay, usually it is done in postgraduate chemistry department course. Opposite here. Okay, so now let's move on with what you did in hydrogen atom-like problem. So more carefully, we want to solve this. For 3D central force problems, we can separate our theta phi. The theta phi part is always spherical harmonics. Sorry about that again. I think I should have used because it is nuclear motion, this instead, okay? But here we are not talking about the electron thing, so that should not lead to any confusion. But that is really what I meant. Secondly, it is more convenient. Stop this. Secondly, it's more convenient to write the radial part as 1 over r times an other radial function. This whole thing is the radial function, okay? But in solving central force problem, it is advantageous to do something like this. Another point I would like to make is that you have YLM theta phi here, and this radial function formally depends on two quantum numbers, n and l. All right. Now, next step is to plug this thing into this 3D equation. Okay. Also remember, the Laplacian in 3D has a lot of things. There are terms with DDR, bracket DDR, things like that, a second derivative at the end. And there are terms that has to do with the angular momentum things, theta phi operators, derivative operators. So now you substitute that into the Schrödinger equation. You see that there is a term L squared over 2 mu R squared. When operate on YLM theta phi, it will give this extra term. But now with the R, it will go into the radial equation. Okay, so here I only write down the radial equation left. The angular part for any central force problem should not be solved again and again. The answer is YLM theta phi. But there is an extra term that goes into the radial equation. This is not quantum mechanical. If you do central force problem in classical mechanics, this term is also there. Only it is L squared divided by 2 mu R squared. So this is the remaining one variable Schrödinger equation in R to solve. So what we did is, what we have done is this thing. I already told you about it. So next, we really want to get the answer without doing anything more. Now, formally, this part, this term has R in it. Therefore, the whole landscape is now this quadratic thing plus something contributed by the rotational motion. This is what I meant by, in general, the vibrational part is coupled with the rotational part. The next thing we would like to do is approximate this R by R0. Once we have this to be the equilibrium separation, this becomes a constant, a number. Therefore, we can again put it to the other side and handle it later at the end. It becomes a number. It just shifts the whole landscape of the harmonic oscillator. All right, so that is convenient. So let's do it. Now, for the very mathematically inclined students, you may want to treat this whole thing together. But I'm not one of them. So now let's think about the physical picture. So if I set that right at R0 for the rotational thing, I am left with a harmonic oscillator about R0. Okay, now with this is now a radial direction. Okay, and it is not vibrating about R equals 0. It is about R0 somewhere away, and it is only small amplitude vibration there. All right, so if you shift from 0 to here, it is really a single one-dimensional harmonic oscillator problem. What is the frequency? I mean the omega. It is the spring constant divided by reduced mass square root. So if we can, from experiment data, obtain where this vibrational frequency occurs, we could use the data and calculate the spring constant, which is a characteristic of the bond. All right, the origin comes from the electron's motion. The rotational part, as I already mentioned, there is a quantity called the moment of inertia involved. If we can read out from data what is the moment of inertia, thereby we could obtain the equilibrium separation. Okay, so let's make this approximation. We don't like this to couple with the vibrational motion, thereby we approximate this by R0. Then it becomes a number. But notice that it depends on the quantum number L. So we do that, we put this term to the right-hand side. So again, we are left with a single variable harmonic oscillator problem. This is a harmonic oscillator, eigenfunction, then this is the eigenvalue, the whole thing, eigenfunction. Okay? At this point, we don't need to do anything anymore. We know these are vibrational state center at R0. The allowed energies are n plus half h bar omega, and omega is k divided by mu square root. Okay, done. You see, so what we are saying is the following: this whole thing is the eigenvalue of the vibrational problem, and it is given by n plus half h bar omega. Okay, so finally we put these two things together with this term, we get the final answer. Okay, now if you don't like the last 3 pages, too many Schrödinger equation, don't worry, we are doing applied quantum mechanics. This final answer is the most important take-home message. So let's look at what it is. Okay, you don't like the mathematics, you must like the following pages that comes. So the left-hand side now gives you the allowed energy of a molecule when the molecule lives in the lowest binding curve due to electrons. That is generally the case. The first term is just a number. It is the bottom of the binding curve, right? But on top of it, there are 2 more quantum numbers. There's a vibrational quantum number that starts counting from 0. Remember, oscillator counts from 0, okay? Half h bar omega is the ground state energy. And then there is a rotational term with a quantum number L. Just like your hydrogen atom problem, you have an N and an L, okay? So when N is 0, you could have L equals 0, L equals 1, L equals 2, L equals 3, and so on, okay? Similarly, when N is 1, you could have L equals 0, L equals 1, L equals 2, and so on. So these are called vibrational energies. These are called rotational energies. It is quite like sending a postcard or a letter to your friend. Okay, your friend is a molecule, but you have to state where this molecule, which energy is it. Okay, so roughly speaking, it is New Territories. Okay, CUHK main campus, and here is a science center, something like that. Okay. So this is the whole form. And the full motion, the wave function of the nuclear motion is given by the radial part. This thing is the oscillator states. Remember, we factorize a 1 over r so that the equation at the end looks like a oscillator problem. You see? Okay. If you don't do this, you just call something radial function. The form is more complicated than that. But of course, at the end, it is an oscillator problem in one direction. So here is the nuclear wave function. All right. Now, again, it is important to realize that it is an oscillator centered around the equilibrium separation. And it turns out that this 1/r prefactor, this factorization out of 1/r is important for you to understand transitions. It is because for transitions between atomic states, the basic mechanism or the most important mechanism is electric dipole moment. Similarly, you play with light. So again, the most important mechanism for transitions between molecular states is again electric dipole moment, but now of the molecule. So you need to know this, because when you want to think about whether a molecule can go from n equals 0, L equals 1 to n equals 1, L equals 2. So there are two molecular states. Can it go up there? Then you need to look at, there's an initial state, there is a final state with the molecule's electric dipole moment in between. Thereby, at that time, you need to at least realize the initial state is something like this, the final state is something like this, but with a different N, L, and so on, okay? Next, it is an important piece of physics. And at the end, I hope that you also appreciate nature is very kind to us, physicists and chemists. What I want to say is the following. We have three terms, but what I want you to take home is the following. These three energies turns out to be very different in magnitude. This is very small, the rotational one, very small, 0.001 eV or even smaller, 1/1000, okay, or smaller. The vibrational thing is something like 0.1 eV, something like that, okay? 1/10 eV. It's slightly hot, warm, something like that, okay? In thermal physics, you know, room temperature is 1/40 eV, okay? So warm is about vibration. And the last thing, you know, that signifies binding of the molecule. And in the early pages, I show you a column of number, binding energy is 5 eV, 7 eV, that order. So the first term, the number is, take it as 10 eV. Vibrational one is 0.1 eV or so. So already 1% of the first term. The third term, rotational, is 1% of the vibrational term. Therefore, it's 1% times 1%. So 1/10,000 of the first term, okay? So take this with you, okay? If you don't want to understand why, at least take this with you. The three terms are very different in typical cases. It's very different in energy in typical cases, okay? So here I want to explain a little bit why so, okay? The advantages, the advantage of having this separation of the energy scale is that we can do microwave experiment on a gas of molecule, and we are quite sure that all this transition must have to do with transitions between rotational levels only. If we do infrared experiment, then we need to worry about transition between vibrational level. and so on, okay? Only when you shine ultraviolet or even higher energy light into it, you can go up to the higher electronic curves. Usually that will dissociate afterwards, okay? So let's have a sense of why so. Estimate the numbers. Here, very dirty, no equal sign. It is estimating the order of magnitude. Now, the first thing I would like to point out is the following. So this is binding energy. You know that it is 5 dB, 7 dB. So if you are happy with that, go, fine, go to the next page, okay? Or if you think about taking the molecule from the lower electronic curve to the higher electronic curve, they call it energy B prime. Again, it is 10 eV or even bigger. A quick estimate of this energy using a little bit of quantum mechanical knowledge is the following. After all, the electron living in a molecule is confined in space, right? The fact that an electron lives with these two nuclei, we know the bond length is about 1 angstrom or so, LCAO, too far away, they don't feel each other, right? So R0 is about 1 angstrom, and the electron must be living in this surrounding. So the electron is confined in this region of this size. It's like a particle in a box problem. So a good estimate will be h bar squared divided by mass of electron. How big is the linear size, angstrom, okay? So you plug anything of this thing, and then you put any order like this. At the end, you will get 5 eV, 10 eV, that kind of things. Okay, so we are done. The first term, the number there is many eV. It's too big for us to worry about it, basically, because experiments usually are done in the infrared and microwave. How about the second term, the vibrational term? There are many ways to think about it. I will use a dirty thing. So I'm thinking about it this way. So let's say this is parabolic, and then I draw it all the way to the binding energy height, okay? So I know that this is of the order of the electronic thing that we estimated on the last page. And then we know that it is half spring constant and then some length square. That is the energy of a spring. You compress it that much. So how much you can compress it? Very rough estimate is K times the bond length square. You compress it to the largest extent, okay? So that will be an energy for us to estimate this vibrational K, and therefore we can have the frequency, therefore we can have a typical H bar omega. So very rough indeed, but the answer is reliable. So we simply, I don't even care about 1/2, okay? So K R0 square is roughly the binding energy. I mean, this height, okay? So therefore, we know that we can estimate what K is. With K, we can relate it to omega square. So therefore, we have a relationship from here. After replacing K with omega, this is the estimation from which we can solve for omega, okay, which is this expression, okay? But the nice thing is that, again, I can factorize out h bar over r 0 square. This appear in the electronic thing. Okay. Now you see why it is smaller. Because we are handling nuclear motion, we have nuclear mass down in the denominator. The nuclear mass is much bigger, okay, 10,000 times usually, than the electron mass. That's why electronic energy is big, because this is electron mass. But now we estimated that omega goes like 1 over square root of the nuclear mass. Okay, so instead of electron mass alone, now we have a nuclear mass which is much bigger, making omega much smaller. That is the key physics here. So typical vibrational energy is by the harmonic oscillator h bar omega, the interval. Therefore, this is given by the electron's typical energy, that is a few eV, 5 eV or so, but multiply into a ratio which is small. This ratio is the electron mass ratio, the electron mass divided by the nuclear mass square root. Okay, what is this? The electron mass over nuclear mass is typically 1 over 10,000 or even 20,000, depending on the atom. If it's bigger atom, this ratio will be even smaller. Okay, H2 is the worst. Okay, but nonetheless, at least a proton is 2,000 times heavier than electron. Okay, so if you have 20 nucleons, this thing is easily 1 over 20,000 or so. All in all, taking into account of the square root, I would say this thing is around at least or smaller. Okay, 1% is the ratio. So an easy way to remember it as electronic thing, 5 eV, 10 eV, h bar omega vibrational is 1% roughly of that energy. Okay, so thereby we can say the vibrational energy typically is 0.1 to 0.01 eV. If you want a range in the EM spectrum, it is around the infrared. How about rotational? The last term, it is L squared divided by twice of the moment of inertia. This is L times L plus 1 h bar square. I don't care about those L times L plus 1. So it is 2, it is 6, and so on. So it's all some number. Okay, doesn't matter. The key thing is h bar square divided by 2 mu r0 square. Now mu is entirely the reduced mass of the nuclear. So if we divide m here, we multiply by m, you see again, this is the electronic energy, 5, 10 eV. Now it must multiply by a factor which is m divided by mu. We don't have the square root here, you see? Now, this has a square root that makes it 1%. Without the square root, thereby it is 10 to the minus 4, or 1% times 1%. Okay? Given that this is 10 eV, rotational thing refers to energy scale 10 to the minus 3 to 10 times minus 4 eV. If you take 10 times minus 4 eV, it falls onto the microwave range in the EM spectrum. So take home message, summary. These 3 terms correspond to very different energies, and it gives us a lot of advantages. in analyzing molecular spectrum and doing molecular spectroscopy. And also, this separation of energy scales further justified the Born-Oppenheimer approximation that we start with, okay? Very different energy meaning very different velocity, very different motion. The electron is very rapid, the nuclear motion is very slow, even if you think about it classically. Therefore, electron motion, in consideration, we can fix the nuclear as certain separation. You also must remember this number. I think you need it in thermal and statistical physics course. So room temperature is about 1/40 eV, a very handy number to play with. I think this week's sample question has this thing in it as well. So let us look at this big picture again. What we did is the following. The first term is this number. So therefore, we take this, blow it up. The second term has n equals 0, n equals 1, n equals 2, n equals 3. These are these horizontal lines, okay? And h bar omega is here, okay? This is 0.1 eV order, get me? Now on top of it, we have the third term. The third term is like this, but the typical energy, h bar squared over I, or 2I, is 0.001 eV. Now, it becomes a challenge for me to draw something on it. That's why this is not to scale, okay? This is exaggerated. For n equals 0, start counting L from 0. So you have a L equals 0 line that at the same energy as the n equals 0. Then you have a L equals 1, L equals 2, and L equals 3. Nonetheless, remember, this spacing is of the order of 0.001 eV, while this thing is 0.1 eV. So I should have just drawn maybe 20 or so in this range. But here I only draw 8 of them. So it's exaggerated in the picture. Get me? But this is not all. You may start from n equals 1. You have an other multiplet of the rotational state. So this rotational states live with the n equals 1 excited vibrational state. Then you go to n equals 2, there's an other multiplet, start from L equals 0, and so on. Do you understand? Okay. Now, what are these lines? These are molecular levels. A molecule can take on any of this energy. It is discretized, but quite dense, okay? So you go there, then you know the wave function. The electronic part given by this line. Vibrational is a harmonic oscillator wave function, and then L equals 3 here, okay? 0, 1, 2, 3, 4, okay? Then you know it's Y4M theta phi. And M runs from 4 to -4. They are hidden degeneracy, okay? So I think that is the big picture I want to convey. So let's take a break. The next thing is transitions. How to look at the transitions between these states. That will take us to a discussion on molecular spectrum at the end, okay? So let's have a break now. And then I need to solve some technical problem on my computer.